So, in this lecture we continue our study of the black hole and star-like solutions. In particular, in this lecture we're going to study so-called Oppenheimer-Snyder collapse of a star into black hole. So we assume the following situation, that before that for t less than 0, we have a ideal ball, which is standing at a radius r0, and there is inside it energy moment, non-zero density and non-zero pressure. Say pressure is due to thermonuclear reactions that are going inside the black hole. And for t greater than 0, the fuel, the thermonuclear fuel, is spent entirely, and the collapse starts. So the ball starts to shrink. And well, before t equals to 0, the solution is exactly the same one as we have been considering in the previous lecture. After the moment t equals to 0, we consider the approximation that was used by Oppenheimer and Snyder, that p equals to 0. So we have a pressureless dust, which means that energy momentum tensor is rho times u mu u nu. And we assume that the dust here is spatially homogeneous. So, but due to the collapse, its density is time dependent, so this is a function of proper time only, and nothing else. And outside of the star, always we consider t mu nu equals to 0, and lambda everywhere is 0, cosmological constant is 0. Well, we consider ideal spherical symmetry, and even during the collapse process, we assume that there is no any violation of homogeneity of the dust distribution inside the star, and ideal spherical symmetry. Of course, this is a very crude approximation, because any violation of the spherical symmetry or the homogeneity of the dust distribution, dust density inside the star, will grow with time due to tidal forces, due to the gravity, if there is some violation of the spherical symmetry, due to tidal forces, because this part of the body is attracted to the center stronger than this part, well, this perturbation is going to grow. This is due to tidal forces. Of course, so we assume some very crude approximation. But in this crude approximation, we have the following situation. Because of this ideal spherical symmetry, outside of the body of the star, we always assume to have Schwarzschild metric, due to Birkhoff's theorem. So outside of the star, we always assume that the metric plus corresponds to that. This is a metric outside of the star. We always assume to have the following metric: dt squared minus dr squared 1 minus rg over r, this one, minus r squared d omega squared. And rg is equal to 2 kappa m, where the m is the mass of the star, the total mass of the star. So, due to the ideal spherical symmetry, there is no gravitational radiation. Why? This is the argument behind this fact is the same as we have been discussing at the very end of the previous lecture. So let me repeat this argument again. Assume that you have an ideal spherical body with the homogeneous electric charge distribution inside it. And assume that this ball of the charge starts to shrink, acceleratively shrink. In such a way that the homogeneity of the charge distribution and spherical symmetry is not violated. Because this ball, independently of its radius, creates the same Coulomb field outside of its body, we have non-zero electric field, but zero magnetic field. As a result, there is no radiation, despite the fact that during this shrinking, there is an accelerative motion of electric charge. Despite the fact that we have an accelerative motion of the electric charge, there is no radiation in such an ideal situation. The reason for that is the following, that to have electromagnetic radiation, one has to have at least dipole moment changing in time. While for the ideal spherical symmetry, have not only dipole, but all the momenta, all the multiple momenta with respect to the center of the ball are zero. With respect to the center of the ball are zero. So this is the situation with electromagnetic radiation. With the gravitational radiation, the situation is even more refined in the sense, well, first of all, there is no radiation also, even can be guessed within Newtonian approximation, because independently of the radius of such a ball, outside of it, it would create a Newtonian limit, just Newtonian potential. Independently, the same Newtonian potential corresponding to the same mass, as if it is situated in the very center of the ball. So this is the essence, again, of the some kind of revelation of the Birkhoff theorem, that independently of the size of this guy, if the spherical symmetry is never violated, we have outside of the ball the same Schwarzschild metric with fixed mass. Intuitively should be understood that if there is no energy fluxing out, the total energy of this ball remains constant, and the total energy of this ball is just its mass. Okay, that's the situation we have. But at the same time, the surface, the radius of this ball is a function of time. The radius of the surface of this ball is a function of time. So we assume that the world surface of the surface of the ball is as follows. It's the following vector. So it's t of tau and sigma of tau. And we should stress that throughout this lecture we assume that we denote by the same sigma, we denote two different things, both the world surface of the surface and the surface of, so world surface and surface of the ball at the same moment. I hope it will not cause confusion. So in spherical coordinates, this guy occupies all the angles θ and phi, staying, which define this metric, and r as a function of proper time at initial moment of time t0 is r0, this r0, which is greater than rg, such that we have actual star rather than a black hole. So the radius of the star initially is greater than its gravitational radius. So this is the conditions. Inside the star, inside here, during the collapse processes, so in this moment, before t equals to 0, the solution is the same as it was in the previous lecture, but after t equals to 0, here we have the following metric, ds minus squared, so inside the star, minus for the inside, d tau squared minus a squared of tau, d chi squared plus sine squared of chi, d omega squared. So this is what is this? This is a metric. This metric describes at every given moment, at every dt equals to 0, t equals tau equals constant. So at every given moment of time, it describes spheres of the three sphere. So this is a two sphere, s squared. This is two sphere. Here also, s squared, two sphere. And this total metric is metric on the unit 3 sphere. So this together, so this factor, this metric together with this factor describes sphere, describes 3 sphere with the radius a squared of tau, I'm sorry. And this radius is changing in time such that a gets smaller as time goes by, and r of tau gets smaller as times go by. So we have 2 different metrics inside the star body and outside, and we have to glue them across this surface. So first of all, second derivative of these metrics are fixed by the Einstein equations of motion and are related to the energy momentum tensor inside and outside of the body of the star. We have to glue the values of the metric across the shell and their first derivatives. That's what we're going to do now, and we will find the relation between the parameters of this metric, including this radius, and these parameters of this metric. So, outside the star body, we have the following metric and the Schwarzschild metric. And inside the star body, we have this metric, d tau squared minus r squared times the metric on the unit 3 sphere where chi is running from 0 to pi. Then this metric covers the 3 sphere. And A is a function of tau only due to spatial homogeneity. So we know more or less everything about this metric, I hope. And now we're going to study this metric a bit more closely. Well, I should stress that we're going to encounter this metric in the lecture number 11. So, and we will study it more intensively then. Now we just give a few ideas of how to work with this metric. So, its metric components are g tau tau is 1, obviously g chi chi is minus a squared, g theta theta is minus a squared sine squared chi, and finally g phi phi is minus a squared sine squared chi sine squared theta. Okay, so one can easily calculate Christoffel symbols for this metric. The relevant for our discussion here are the following ones. Gamma 0 ij is a dot ag twiddle ij, and gamma I 0j equals to a dot a delta ij, where I and j run from 1 to 3, and a dot is dA over d tau, and here jij twiddle is just the metric on the unit 3 sphere, so it's just this metric, so it's equal to d chi squared plus sine squared chi d omega squared. And of course there are non-zero components, hence due to this metric we have non-zero components of the Christoffel symbols like this, which are just the same as for unit 3 sphere. And we don't need the explicit value in this lecture, so we discard them throughout the discussion here. We give this metric in great detail again in 11th lecture. So all we need is to know these components of the Christoffel symbol. All the other components either trivially follow through due to symmetries of the Christoffel symbols from these ones, or just zero. So as a result, due to these values of the Christoffel symbols, the 0, component of the Einstein equations of motion, so is like this: 3a squared a dot squared plus 1. So this is just equal to this for this metric ansatz. And also, due to the fact that T mu is equal to rho of tau u mu u nu, in this metric, the dust is fulfilling a free fall. So in it's basically in the coordinates in d tau, when d tau is fixed, the dust is stationary. Well, it means that, in all, I mean that u mu for velocity in this metric is just 1, 0, 0, 0 for the dust. And as a result, the only non-trivial, non-zero component of the energy momentum tensor in this frame is T0 equal to rho of tau. As a result, we have the following equation. So for this metric inside the star, we have the following, this Einstein equation, this component of the Einstein equation. Has the following form as a result. Rho a squared. These components of the Einstein equations, because we have this 0, are trivial. So they just establish trivial relation 0 equal to 0. And as we explained in the lecture 3, instead of sum of the components of the Einstein equation, we can use energy momentum conservation. So we're going to use it here. In the present situation, for the metric tensor that we have, it has the following form: rho u mu u nu plus gamma mu beta mu rho u beta u nu minus gamma beta nu mu rho u mu u beta. And we have 4 equations for each value of nu. We have 4 equations. And hence, if nu is equal to 1, 2, 3, we have trivial, again, we get trivial relations at 0 equals to 0. While for nu equals to 0, we obtain the following equation, that rho dot plus 3 a dot over a, rho is equal to 0, where rho dot is a time differential of rho. And as a result, this equation is equivalent to d tau of rho a cube is equal to 0. So, which is obvious equation, which states that as a is shrinking, as the radius of the sphere is shrinking, its density of the dust inside this sphere behaves as a constant times a cube. So reducing, density is increasing, radius is decreasing. As the volume decreases, the density is increasing. If we fix this constant, as a result, we obtain the following: rho a cube is equal to 3 8 pi kappa a 0. And as a result, the solution of this equation, can be represented as follows, parametrically represented as A of eta is equal to A0 over 2, 1 plus cosine eta, while tau of eta is equal to A0 over 2 eta plus sine eta. Again, we're going to study this metric in greater detail in the 11th lecture, and we'll understand the physical meaning of this parameter eta, which runs from 0 to pi. So eta is running from 0 to pi. And the physical meaning of this parameter will be studied in greater detail in that lecture. But now we can just show that this indeed solves this equation. In fact, it's not hard to see from here that d tau over d eta is nothing but A, just after differentiation. As a result, from here, one can see that dA over d tau, which is dA over d eta over d tau, is equal to dA over d eta 1 over A. Using this equation can be represented, so this equation can be represented in the following form. dA over d eta squared plus A squared equals to A0A. This is nothing but oscillator type equation, and one can easily show that this guy solves this oscillator type equation. Now, what does this solution describe? It describes the following situation, that when eta is equal to 0, tau corresponds to 0 also, which corresponds in this coordinate, which corresponds to the time equals to 0. This is the moment of time when the collapse begins. This is a moment of time when all the thermonuclear fuel is spent, pressure is switched off, and the collapse starts. At this moment, A of eta is equal to A0, as can be seen from here. But as eta reaches pi, A goes to 0, so the sphere shrinks to 0, shrinks to the singularity, and this is reached within finite proper time. This tau goes to pi A0 over 2. So within finite proper time, the surface of this sphere crosses the horizon, crosses r equals to rg. We didn't yet see that. We're going to see that in a moment when we will glue these two metrics. And the body of this star shrinks to 0 size within finite proper time and reaches the singularity. So this is the solution describing the collapse. Now we are ready to glue this metric to this metric.